So welcome to the session on modal types. So before we start, I have an announcement. So apparently someone forgot a jacket which has Galois marked on it somewhere in the room. So if you recognize it, you can come and fetch it later. The first speaker is going to talk us about, so this session is about modal types. Modal types have all sorts of useful applications, but they're not actually that easy to implement and type check. And so Daniel Gratzer from Aarhus University is going to tell us how you can do that.
OK, so from the start, is the audio OK? Everyone can hear? OK?
What?
Yeah. I walked into that one, that's fair. OK, so this is some joint work with Jonathan Sterling and Lars Birkedal. So let's just get into it. So concretely, what I'd like to do in this talk is discuss adding a single modality to Martin-Luft type theory, and that modality is box. So the intuitive behavior of box is that M is supposed to be of type box A, when M is basically of type A with an extra proviso. And that proviso is that M doesn't mention variables that are not themselves boxed. So it's elements of A that are restricted in some way so that they can't depend fully on the context. And this does arise naturally in programming, sort of, which is that in stage programming, for example, we can use box A to represent a previous stage. And the dependency requirement is the insurance that a compile time computation doesn't depend on runtime input or something else that would create problems. In Modal FRP, which I expect we hear about later, we can use box A to represent stable types. And in distributed computation, we can use box A to represent the computations that can be moved freely in between nodes because they don't have a node-specific resource in their dependencies. So these are all very interesting applications. I'm going to not talk about any of them. Instead, I'm going to abstract a little bit, and I want to focus on box just as a sort of unifying abstraction on top of all of these different things. And so from a sort of categorical perspective, I want to think about box as just some comonad with some particularly nice properties. So in total, our contribution is MLTT sub lock, which is a full Martin-Luft type theory, which has all these sort of standard connectives, sigma, pi, nat, intentional identity types, a cumulative hierarchy of universes, and it also has the box modality. And we've constructed a precise syntax and worked out some syntactic meta theory for for MLTT sub lock. We've also proved the decidability of type checking and actually implemented it. So why is it hard to add modalities to a type theory? So the general reason is that modalities like to mess with the context, and this tends to break things that we enjoy in type theory. So a simple sort of first approximation of what we might expect for box as an intro rule is that when we're trying to construct something in box A, we look at our context and we divide up the context into two halves. There is the half which is under a box, so that's box gamma, and the half which is not, which is delta. And then we just say, well, drop whatever is in delta. We're not allowed to use it when constructing this M. And this clearly accomplishes the goal of making sure that we don't depend on anything that's not under a box. But it's going to break some important syntactic properties of our type theory. In particular, it's not going to be the case that we can push substitutions under this connective. And this, along with many other failings, is going to prevent us from really constructing a good account of this type theory. So there's work on taking this rule and sort of souping it up to make it a little bit more tractable. But we're going to opt for an entirely different approach, which is just adding judgmental structure to incorporate what box is supposed to mean. So we're going to try the Fitch-style judgmental structure, which basically involves adding something to our contexts. So contexts are no longer just lists of variables. Instead, they're interspersed with this lock symbol. And the lock symbol it's a tag saying we're not allowed to use anything behind it. So if you look at term/var, you can see that the rule for accessing a variable has this side condition which says, OK, you need to get out a variable. It has to have the right type. But also, it can't be behind any locks. And if it is, this rule won't apply. So now it's a little bit simpler to decide what the rule for box should be, because we have this lock that we can use to tag the context as inaccessible. So rather than trying to remove all the things we're not supposed to use, we just add this lock, and that tells us that we're not allowed to use anything behind it when constructing this M. But this can't be it, because currently, once we put something behind a lock, it's just gone forever. And that sort of defeats the whole point. So we also need a way to remove the locks. And that turns out to be the elimination rule for box A. So I'm going to read this from the bottom up. So if we're trying to construct A in context gamma, then we can delete all of the locks from gamma. That's that gamma soup unlock. So we remove all the locks from gamma, all the variables become accessible. But we're no longer just going to try and construct A. Now we have to construct box A. So the context becomes easier to work with, but the goal becomes harder. So this turns out to be the elimination rule that we want with box. And with this, we actually have a calculus. And we can show that we can formulate a calculus of substitutions, and that substitutions are able to actually commute past these connectives. This isn't obvious, but it turns out that it can be proven. So a small programming break. I said at the start that I wanted comonads. And I've given you two operations, but they're not the operations of a comonad. So how can we actually implement what I was talking about at the very beginning? So I have up here the code for extract, which takes us from box A to A. And the idea is we just use the elimination rule for box. It has the side effect of removing all the locks from the context. And in this case, there won't be any locks in the context, but that's perfectly fine. So now let's go through constructing one of these together. So duplicate box A to box A. So we start with this variable x in scope, type box A. We're trying to construct box A. We hit it with the intro rule, and that adds a lock to the context. So x has become inaccessible for the moment, and our goal changes to box A. Hit it with another intro rule, and now we're trying to construct A, and we sort of want to use x at this point, but we can't. It's locked away. So now we turn to the unlock rule and use that to get rid of the locks in our context. That shifts our goal from A to box A, but that's totally fine because we have box A as the type of x. So now we just plug that in, and we're good. So this gives us the comonad operations, but this isn't enough, right? We don't just need elements of this type. We also need certain equations between these operations. And this brings us to the most fiddly part of designing a type theory, which is we have to decide what the definitional equalities will be in that type theory. And this is fundamentally a balancing act. The more definitional equalities that we can add, the easier proving things will be, because definitional equalities are precisely what the proof assistant is going to handle for us. At the same time, if we add too many definitional equalities, type checking will become undecidable, and without radically restructuring our implementation, it's going to be impossible to implement the type theory. So for MLTT sublock, with box A, we're sort of in the best possible situation that we could hope for, which is that we get both a beta and an eta rule. The beta rule, the one on the left, says that if we lock something and then unlock it, those two operations cancel. The eta rule, the one on the right, says that if we have anything of type box A, we can phrase it as a locked something. So in this case, a lock of an unlock. And this is a definite win from the Fitch-style presentation of this calculus. Normally, modalities are designed not with this unlock operator. They're designed with this sort of let eliminator, a sort of pattern matching operation. And once you have that, in order to get these eta rules, you actually have to introduce what's called commuted conversions into your calculus. And this is significantly more challenging, particularly in order to prove normalization. So that's a win. But it's not entirely for free. The premises from these rules are actually subtle. So if you look at the bottom, the implication that I have there, if this term on the left is well typed, then the term on the right might not necessarily be well typed. This tells us that eta contraction actually fails in general for box. And this poses significant challenges for deciding conversion, because eta contraction is one way that you might hope to do this with like a rewriting system or something like it. So after careful consideration, we have to show that if the premise holds, then both sides of the equality are well typed. And that means that the tops of these rules are not just a detail. They're actually important, and they come up later. So taking stock, at this point, we have MLTT sublock as a calculus. It's declarative, but it contains all the things that we wanted. And we can actually start to develop the meta theory of this calculus. We can prove that substitution and presupposition and all these other things hold. We can also show these more modal admissibilities. So we can show that locks behave in the way that we can expect, that having one lock is just as much of a problem as having two locks, for example, sitting next to each other. We can show that lock strengthening holds, as well as various forms of exchange. And this is not just routine calculation necessarily, because this all happens in the presence of all of these other connectives and all of the other rules of our type theory. And these last two bullet points, they're admissibilities. And admissibilities are fundamentally non-local properties. When you add a rule, it's not like you just check that the admissibility is true for that rule. It ripples out throughout the entire system. So when we add these locks to the context, the rules for substitutions all have to be changed, because otherwise we're going to fail to satisfy the admissibility of substitution, as well as other things. So that requires quite a bit of tweaking, but at the end of the day, we can do it. And now we only have one big remaining question, which is, can we actually implement this calculus? Can we write down a type checker for it? So let's back up away from MLTT sublock and just talk about what it takes in general to implement a type theory. Of course, there are many different ways of doing this, but this is the one that I'm going to talk about because it's what we did. So if we're trying to implement T, some type theory, what we might start by doing is constructing a bidirectional syntax for T. So this is a restriction of the syntax so that not all the rules are available all the time, but it makes the calculus more syntax directed so that we can generally figure out what rule we're supposed to be using. And after we construct that bidirectional syntax, we look at T again, and we prove that T satisfies a result called normalization, that every term in T can be canonically presented. So there's a canonical member of every equivalence class up for conversion. More on that later. Once we have the normalization result in hand, we can prove that conversion in T is decidable. And with the decidability of conversion, we can actually show that type checking in the bidirectional calculus is decidable. So now we have a calculus which at least has the letter T in it and has decidable type checking. This seems like it might be enough, but it's not quite sufficient because the bidirectional calculus might be too restrictive. It might not let us express every term that we started with. So we also need a sort of completeness result, something that tells us that every declarative term can be put into the bidirectional calculus so that we can type check it. And once we have that result, then we have that the bidirectional calculus sort of faithfully represents T, and because it's type checkable, it's implementable, and now we have an implementation of our type theory. Throughout this process, we rely quite heavily on the admissibilities. For example, the normalization result is just not possible to prove if your calculus fails presupposition. So let's talk a bit more about the bidirectional syntax. So one of the benefits of designing our calculus in this Fitch style is that it's a fairly minor extension to MLTT in some sense. The syntax looks fundamentally the same and all of these other things. And so we can reuse the existing work on bidirectional syntaxes for MLTT. So we split our terms into two distinct categories, those that we check, those that we synthesize. We split our type checking judgment into the checking and synthesis phase. So the idea is that the checking judgment, it's best thought of as a function of 3 arguments, context, term, type, and it returns true or false. The synthesis judgment is going to turn into a function of 2 arguments, context, term, and return a type if one exists or an error if one does not. And within this framework, we can add 2 new rules corresponding to the 2 new connectives for box. We add a checking rule for lock and a synthesis rule for unlock. And this corresponds to the general intuition that we have with type theories, that we check intro forms and synthesize elimination forms. More details on this in the paper, of course. Now, the payoff of doing this is that we can reduce the decidability of type checking in MLTT sublock to the decidability of conversion in MLTT. Sorry, I got that backwards there. The decidability of type checking in the bidirectional calculus reduces to conversion in the declarative calculus. So how do we prove that? We use normalization. So the normalization function is just a function from terms to terms on type terms, satisfying some properties. And those properties basically boil down to the following result, which is that if we want to check whether 2 terms are convertible, it suffices to check whether their normal forms are identical. And since checking normal forms for literal syntactic equality is definitely decidable, if we can write down this normalization function, we're in good shape. And the way that we do that is using a term called normalization by evaluation. I have absolutely no time to talk about it. It's very interesting, though, I promise. So I'll just present this sort of high-level slogan, which is that we separate our normalization function into 2 stages. First, we take our syntactic terms and we evaluate them to some sort of computational domain. And then we quote those things back. And in the process, we get normal forms. So the evaluation performs beta reduction, and the quotation handles eta expansion. And the result at the end of the day, beta normal, eta long terms. Now, quotation is fundamentally a type-directed procedure in normalization by evaluation. And that's important for us, because that's what we need in order to handle these type-directed rules like the eta expansion for box A. So that's why that sort of scales to support modalities in a nice way. What isn't quite so nice to scale is the proof. So the proof of normalization by evaluation being correct usually breaks into two parts, showing that it's complete and showing that it's sound. And both of these are fairly involved proofs. So the first one involves constructing a per model, and the second one involves constructing a Kripke cross-language logical relation, which is more annoying than it sounds somehow. And thanks. And in order to handle our modality, we actually have to introduce an extra layer into this. We need Kripke worlds in order to interpret what the modality is supposed to be doing. So we actually end up with a Kripke per model, and the Kripke logical relation becomes even more Kripke. And I lack a good word for this, so double Kripke cross-language logical relation. And the main sources of complexity here are actually not just the modalities, but remember, we have this full dependent type theory, and universes are very, very much a source of complexity in this proof. We don't just have a per model, we have a hierarchy of per models, one for each universe level. We don't just have a logical relation, we have a hierarchy of logical relations, one for each universe level. And these interact in order to interpret universes. But we've done all that, and so at the end of the day, we end up with a normalization algorithm for MLTT sub loc. And from this, we can inspect the results and write down a grammar for normal forms. And the payoff of this is that we can now reason about the existence of terms by induction on normal forms. So for example, we can show that there's no term going from A to box A. Such a term would sort of trivialize our modality. We can show that this doesn't exist because if it existed, it would have a normal form. And if it has a normal form, then it fits into this very restrictive grammar. And simple induction over that grammar tells us that no such term exists. Moreover, with these normal forms, we can show that type checking in the bidirectional calculus is sound and complete for type checking in the declarative calculus, which gives us the declarative type checking, or the decidability of type checking that we wanted at the very beginning of all of this. So this is the foundation for implementation of MLTT sub loc, and to our knowledge, this is the first such result for a full dependent type theory with this sort of modality. So with that in mind, I think I'm done.
Thank you, Daniel. You can, of course, ask questions through Slido. So let me start with a question from Slido. So can your theory be made to work with untyped conversion?
Well, potentially. The one answer is that I don't have a particular strong preference to do this, and I think it would complicate the eta rules. However, if you're willing to drop the eta rules, then I suppose that it should be possible, yes.
There's another question on Slido which I found interesting. So can you relate your calculus to sort of standard calculi for multi-stage languages?
First, well, I believe so. Currently, we only have a single box modality, which makes it maybe not as rich as you would find in many multi-stage calculi. But I'm hoping that this box A should correspond to having a single stage prior to runtime computation.
So were there any interesting interactions between dependent sums and the comonad extension for your NB implementation?
No. One of the nice results is that the cases for the proof were surprisingly modular. Once we had the syntax all worked out, the proof really went relatively smoothly once we had the right theorem statements.
So by proof, you mean the correctness of the NB?
Yeah, so predominantly the correctness of normalization. So once we had designed the syntax and proven the appropriate syntactic meta-theorems, the rest of the proof tended to work out.
Thanks.
So another question from Slido. So I would expect, so André Bauer asks, I would expect mloc to be synthesizing in analogy with, say, REFL M. So I'm not sure I fully understand, but I think André can explain the question if needed. Is it checking because of the placement of the lock onto the context in the premise?
Unlock should be synthesizing, unless I misspoke. Lock should be checking.
Lock? I mean, I think the question says lock, doesn't it?
Yeah.
Lock is checking as an intro form, in the same way that we generally check intro forms. You could, I suppose, reorient it with extra annotations if need be.
Okay, so there was a question from Silvio.
Thanks, that was a very nice presentation. It's neat to see how just fiddling with the syntax can resolve problems, in your case, the introduction of Fitch's trick with lock. I missed something crucial about it. Could you go back to the rules?
Which rules?
The very beginning rule where you explained how locking works. I think it was there. Yeah.
No, I think this.
Yeah. So, right. So you said after you lock something, you can't look behind that lock at all, or you can only look at the box things behind the lock.
No, you can't look at anything behind the lock. The variable rule precludes that. The trick is that you can unlock the context with the while shifting your goal to the boxed thing. So if you have a boxed thing behind a lock, you sort of unlock and then use the boxed variable.
Ah, okay, that was the key trick that I missed.
Yes.
Thank you.
So another question from Skydo is, do you have large elimination?
Yes, we have a full universe hierarchy, and so you can eliminate into universes just like you eliminate into NAT.
So I think we have time maybe for one more question from the audience.
How many pages is the proof?
Can I not answer this question? No. Okay, so the proof roughly breaks down into 75 odd pages. The first 12 to 15 are syntax sort of meta-theorems. Then the per model and then the logical relation are relatively evenly divided with the rest.
Okay, so maybe while the next speaker gets ready, there's maybe the most important question yet is from Andre Bauer again. So how do I get the lock symbol in LaTeX?
Oh, you know what? I forget. It's not Tixie. There was some package that let me do this.
Cool. So, so before I introduce Pierre-Marie, there's a service announcement. So the last